Hey everyone, it's me, Miss B, and we are looking at today the Unit 5, Lesson 10, Cumulative Practice Problems for Illustrative Math, Algebra 1. So let's look at this first question. We have a store receiving 2,000 decks of popular trading cards. So the number of decks of cards is a function D of the number of days since this shipment arrived. Here is a table showing some values of D. So we want to calculate the average rate of change for the following intervals. Day 0 to day 5 and day 15 to day 20. So from day 0 to day 5, we're going to look here and here. So it's not skipping all 5 of these because it goes in chunks of 5. So what we're going to do is do our difference between our inputs and our outputs here. So the input, oops, that's a little too large of a marker. Input is going to be T. And I'm writing a T because I'm saying a T input. And then we have our output. So we're always going to do the difference between our outputs and then divided by the difference between our inputs. So output over input. And then we want to make sure that we're staying consistent with the numbers that we're using. So we always want to go backwards in time, or backwards, well, in time in this case, because it's measured in time, but we want to go backwards in our input values or in the negative direction when we're subtracting. So for this one, I am going to do, for my output numbers, we are going to do the 1,283 and then subtract the 2,000. And then we are going to go in the same direction and do 5 minus 0. That's the general way that you want to do things. However, you can do it the other direction going forward for both. You just have to be consistent. You can't go one direction for one and then another direction for the other. So you either have to go forwards for both or backwards for both. You have to be consistent with which way you do it. But let's actually do the subtraction here. So for the 5 minus 0, that part's going to be easy. It's just going to be a 5. But we need to do 1,283 minus 2,000. That is going to give me negative 717. So this is the start of our average rate of change here, but we're going to try to reduce it as much as possible. So for 5, and it looks like the fraction won't reduce, which, I mean, is kind of obvious, I guess, because this is not a multiple of 5. And the only thing that's divisible by 5 is anything that ends in a 5 or a 0. But we can also just write this as a decimal. So I'm going to express this also as a decimal and say that they're both my average rate of change. So that would be negative 143.4. So both of these are acceptable answers for part A. Now to do day 15 to day 20, that's going to be, I'll do that part in red. And I'll show you that you can do it the opposite direction too. So I'm going to go from 15 to 20, but then I'm also going to subtract in this direction as well. Because we are still decreasing in the number of cards or packets of cards, but you'll see that as long as you're consistent in your direction, you'll still get a negative average rate of change when it's decreasing in value. What happens if you go in the wrong direction or you're inconsistent is that you'll end up with the reverse sign. So if it should be positive, then you would end up with a negative. And if it should be negative, you'll end up with a positive. So we're doing, again, the difference in the output at the top. So output here is going to be, we'll do the 528 minus 338. And then we'll do 15 minus 20 for the bottom. So our numerator, when we do this subtraction, 528 minus 338 is going to be 190. And then for the denominator, 15 minus 20 would give us negative 5. So overall, we still have a negative answer. It's just whether the negative is in the numerator or the denominator. And that doesn't actually change the overall value of this. So having a negative in this case where we just have numbers in the numerator, denominator, or just out front of the fraction itself, all three of those would be the same. So let's put this into a reduced form because it will reduce since 190 should be divisible by 5. If we reduce this, this is actually going to give us a whole number, and it is going to be a negative, so negative 38. Now this is going to be the only acceptable answer for this because it's both the reduced fraction and what would be our decimal answer. So negative 38 is our average rate of change for days 15 to 20. So that brings us to question 2. Now, this is about a study. So a study is conducted to analyze the effects on a deer population in a particular area. F is going to be an exponential function that gives the population of deer t years after the study began. Okay, and so then they're giving us if f of t equals a times b to the power of t, and the population is increasing, we want to select all statements that must be true. So in this case, a is our initial value and b is our growth factor. So when we look at these first two options here, these talk about the growth factor, and only one of these is allowed to be true. So if it is increasing, we want a growth factor that's bigger than 1. That means that option A is going to be correct. B should be greater than 1. And it means that B is not an answer. Now, C and D have two different answers here. So this is another pair of answers where we cannot pick both. So C says the average rate of change from 0 to 5 is less than the average rate of change from 10 to 15. And D says the average rate of change from 0 to 5 is greater than the rate of change from 0 to 15. So the difference here is that this one says less, and this one says that it's greater. And it can't be both at the same time. But since this is increasing, if we want to sketch ourselves a little picture, an increasing function, when it's exponential, and I know my picture here is a little wobbly, this is going to have a smaller rate of change the closer we are to 0. And the further we get away, it's going to be greater. So the answer we're going to choose here is C, because from 0 to 5, that would be like this area, would be less than it is from 10 to 15. So it would follow this pattern, and we would choose C. That means D is not going to be true because they can't both be true at the same time. And the very last one, A is greater than 0. Yes, A is going to be greater than 0 because we can't start with a population of 0 deer and then have them spontaneously increase. So let's give those explanations here. So I'm going to say for A, population increasing means growth factor bigger or greater than 1, because that's what we would need in order for it to increase. And then we're going to say for option C, I would describe this as so how did we word this? Because I gave a wordy explanation for that. The rate of change is smaller. So for increasing functions, so I'll say for increasing exponential functions, for increasing exponential functions, the rate of change increases. I'm going to say the rate of change increases. Okay, and then for E, we'll say cannot start with 0 deer. Okay, so we can't start with 0 deer and population increasing growth factor bigger than 1, and as exponential functions increase, the rate of change is also going to increase. That is going to be it for our first page. We're going to flip our page here and work on questions 3, 4, and 5. So for question 3, we have function f modeling the population in thousands of a city t years after 1930. So that sounds important. I'm probably going to need that number, but I might not. The average rate of change of f from t equals 0 to t equals 70 is approximately 14,000 people per year. Is this a good way? Is this value a good way to describe the population change of the city over that time period? Explain or show your reasoning. So they're giving us a span of 70 years. And they're saying, hey, is that accurate if we describe our average rate of change? What average rate of change does is actually just describe the slope between the starting and the ending points. So they're really asking us like, hey, does that fit? And no, there's a big straight line here, but this curve goes far underneath it. The rate of change is changing. So it's actually pretty flat here, and then it gets pretty vertical as we go on. So I would say it's not, and let's explain that reasoning. So I'm going to say no, the rate of change begins much smaller than 14,000 and it also ends at a much larger growth than 14,000. So, and it is much larger than 14,000 near the 70-year point. Because we wouldn't really be able to keep that average rate of change going forward. It wouldn't help us predict. So we're just saying like, hey, it's not really accurate here. If you're just looking at that one time period, it's not quite accurate, because especially if they're like, oh yeah, well, it was just constantly increasing at that rate. It is much, much different in many different places. I could even draw just 4 separate lines, and these 4 separate easily sketched lines have very different slopes. If I was thinking about all of those as different hills, I would want to walk up this one because it has a much easier slope. This one, I would not even be able to climb because I am not a billy goat or a mountain goat or anything like that, and I would fall straight off of that. Now, this sort of incline the whole way might be a little easier, but it's still going to be tough overall. It's just not a good explanation for the way that that graph changes. So let's keep going. Let's work on number 4. So in number 4, we have the function f, and it gives the number of copies of a book that has sold W weeks after it was published. The equation f of w equals 200 times 2 to the power of w is what defines this function. Okay, so this is what I'm looking at here. This is my function. Got it. So we want to select all domains for which the average rate of change could be a good measure for the number of books sold. So we want probably smaller ranges. So just like how in the last question, it went over a 70-year period, that's a really long time and it was really inaccurate. So we would choose spans that are much smaller in size. So I would say that A works because this is 2 weeks, right? So this is 2 weeks, and it's probably accurate for that 2 weeks. Um, 0 to 7, that's probably a long time, and I'm sure it might curve a lot more over that. So I would not choose B. But for C, C goes from week 5 to week 7, which is also good because this is a 2 week range. 5 to 10 for our next one, that's a little questionable. I would probably say no for that one and no for E. So the only two that where it could be a good measure is just for these shorter intervals from 0 to 2 and from 5 to 7. Especially since it's exponential, it's going to change a lot if we go even further than that. Okay. Yeah. So let's work on question 5. This one is a graph, and it shows the bacteria population decreasing exponentially over time. And we have an equation. So we have a big number, and we have 2/3 to the power of h. So this is what, 100 million times 2/3 to the power of h. That is a second population of bacteria where h is ours since it was measured at 100 million. And we want to know which bacteria population decays more quickly. So we want to compare the two, really, because we have one visual and one actual number. So if I want to know which is decaying more quickly, I am looking at one number here, and that is just the growth factor. So I'm given the growth factor on this one. So that means here we're going to find the growth factor based on what we have in this graph, and then we're going to compare. But that's really the only good way to do this. So let's actually look, and since our first two actually do land on what I would call intersections or like little corners of like actual parts of my graph, I can assign them some values to estimate. Even though I might not be able to see exactly, it does look like it's telling me that these are exact numbers. So at 0, this looks like it has 250 million. And at 1 hour, this looks like it is 150 million. Since they're both millions, I'm just going to compare 250 to 150. So I want to know, and I've shown before, like you should be dividing 150 and divide it by 250. But the reason we do that is because I have 250 and I'm going to multiply it by something. I can use an x here, I guess. Or we tend to use b for our scale factor or our growth factor. So we'll say times b, and that should give me the 150 million. I know I have to multiply by something to create that 150 to move forward. So in order to undo this, we would divide both sides by the 250, which is why, since our 250s cancel out here, the growth factor itself is the 150 divided by 250. So we're going to simplify this because it definitely simplifies. We can, first of all, do some mental math and cross out the zeros and say this is the same as 15 over 25. And then we can also just divide these by 5 and get that our result is 3 over 5. But if you don't believe me, you can plug it in a calculator and see for yourself. So our average rate of change here is 3 over 5. So we're going to comparing 3 over 5 to 2 over 3. So this is just sort of like my work over here, so I'm going to kind of section it off and then write my explanation underneath it. So comparing 3 over 5 to 2 over 3, we want to know actually which of these is smaller because that represents what's going to be left. So if you're not sure how to compare these, you can always put them into decimal form, but 2/3 is actually going to be larger. So 2/3 is going to be around 66%. So if you put these in decimals, it would be 0.66. Actually, just 0.6 continuing, 0.666666666. And then 3 over 5. So this would become 0.66, 0.6, no, not 60, 6 repeating on forever. And this one would become 0.6 and it would end right there. So 2/3 is actually bigger. So I would say 2 over 3. 2 over 3 is greater than 3 over 5. So the smaller one is going to be decreasing faster, which means the graph is decreasing faster. So um, the population shown by the graph is decreasing faster. And that's it. At least for that question, I think we still have some more. Yep, we have 6 and 7 here, and then that's the end of this. So I think we did cut off a couple questions from the original length of this assignment. They generally have you go up to 9, I think, on this one. So we said, you don't have to do 8 and 9. For number 6, they are saying technology required. And that's because it's going to be easier to actually use a graph to do this. So I'll show Desmos for this in a moment. But let's read through it first. We have a moth population, P, which is modeled by the equation P equals 500,000 times 1/2 to the power of W. So I'm just going to highlight that because that's the function I'm using. W is the number of weeks since it was first measured. Oh, okay, so now what was the population when it was first measured? That's what they want us to pull out. That's the initial value part. So that is the 500,000. Now, what was the moth population after 1 week, and then what about after 1.5 weeks? So after 1 week, we could just multiply it by 1/2, and that would give us 250,000. And if they said, what about 1.5 weeks? This is one I would actually want to plug in a calculator. But when we plug it in a calculator, you would get about 177,000. So those are our two answers respectively for 1 week and 1.5 weeks. Now we're going to use technology to graph it and find out when it falls below 10,000. So we're going to switch over here to Desmos graphing calculator. Okay, so we're going to type in our function here. I'm going to say that P is equal to, and this is 500,000, and I'm going to multiply this by 2/3. Nope, 1/2. Sorry, 2/3 was the other question. 1/2, and then this is raised to the power of W. So I can say, actually, I want to define this as P of W. And then I'll have to zoom out to actually show you where all of that is at. So P of W is how I should actually define this. Now, nothing's going to show here because my initial population is 500,000. So while I might have weeks that I want to show here, and you can start to see the actual side of my graph on the right-hand side there, I'm actually going to squish just my y-axis here because my x-axis is okay, but I want this to reach 500,000 so I can see everything accurately. Ah, okay, there's my 500,000. So much better, and I might even have 100,000 here. But if I want to actually find exactly where it reaches below 10,000, we can do this with graphing technology and just say that our horizontal value is 10,000. So I don't think I can just type in 10,000. I don't know if that gives me a line there. Yeah, it doesn't. But you can type in y equals. Um, Even though we don't have like a variable for y in this, um, it might work to also say p of w equals. So let's try that one just to test it out because I'm not too familiar actually. But I can say p of w equals 10,000 and that works too. Yeah, so you can just say that your function value is 10,000. And now we're going to look to find where these two graphs intersect. So on Desmos, that would be if we click on one of them, or we tap on one of them to show it, it shows this gray dot right here. And if I tap on my gray dot, it shows me exactly when they are equal to 10,000. So we're going to round that down to kind of a whole number or an estimate. Instead of saying 5.644, we can actually just round this to like 5.5, and that'll be pretty close. So we can talk about 5.5. So it falls, if we, or actually, you know what, we can be more specific, but we can say 5 point, let's actually go back. I want to use the more specific one, 5.644. So I'll say after, we'll say after about 5.5 weeks. And then in parentheses, I'll put the actual amount, which is 5.644 weeks. Just because I like to kind of get both. Okay, question 7. Give a value for r that would indicate the line of best fit has a positive slope and models the data well. So a line of best fit. This is, yeah, this is more of a statistics sort of thing, but it's still part of our homework assignment. We want to talk about things that fit well or that have a sort of a strong relationship, I guess. Um, I really don't think that we covered this, but I will still give you the answer to this question anyways. If it has a positive slope and it measures your data well, lines of best fit generally go from -1 all the way to +1, where 0 means there is no relationship there whatsoever. So if it's positive and it has a good relationship, it is going to be close to 1. And so I might say that is like um, somewhere between 0.8 and 1. If it was less than that, I wouldn't say it is a good fit necessarily. And then that's going to be it for this homework assignment. So we don't have questions 8 or 9, just these ones. So thank you for sticking with me for this video. This has been the Unit 5, Lesson 10 Cumulative Practice Problems for Illustrative Math, Algebra 1.